Hi, I'm Rain Pullen from the University of Sydney, and I'll be talking through sample G for the sample set. Now, as I have done with other examples, the first thing I like to do is to go through these three tests at the beginning. They're a useful tool for ruling out anything that we need to consider or include in our consideration. So we can see from our unsaturation test, the orange color remains, negative response. The oxidation test was also negative, orange color remained, telling us that there's nothing that can be oxidized. But for the carboxylic acid test, we can see bubbles of carbon dioxide. And this is great news because this immediately tells us that there must be a carboxylic acid present. And that simplifies things a lot. So immediately when we go into everything else, we've got to keep in mind there is a carboxylic acid present. As I have done elsewhere, I'm going to skip IR and mass spec, and I'll come back to those later to kind of confirm some things. And I'm going to move down to the NMRs to begin with. Now, these look very simple, which once again is a nice problem to have. So for our carbon, I'll label this peak 1, peak 2. We can see peak 1 is massively deshielded, all the way down at about almost 180 ppm. Now, if you're looking at a table of approximate areas for different functional groups, we've already confirmed it's a carboxylic acid. So a carbon that's attached to two different oxygens, one of them by a double bond, will be very deshielded. So we know peak 1 is the carbon in that carboxylic acid. Peak 2 is not very deshielded at all. It's at about 20 ppm, which to me suggests that this would just be a regular alkyl carbon that will be probably attached to the carboxylic acid carbon. But we'll go through the motions to confirm this through everything else as well. Now, if we come to our proton NMR, there are two peaks here, though at first you may only see the one, but if we check down in this table, we can see there's two. I'll label this A and B. We have a tiny peak down at about 11 ppm, and then we have a significantly higher looking peak down here at about 2. Now, bear in mind, height is not an important thing. What's important is the peak area ratio. So it's the area within the peak, which is why if we look at this 2, we can see that peak B has 3 protons in that environment, confirming our suspicion that this is a terminal CH3, just an alkyl. And then we see there's 1 proton in this other environment. Now, if we think about our carboxylic acid, there's no other protons in the carbon, but there is a proton on the acid itself. And often with these kinds of acidic protons, you expect to see them fairly well deshielded. They're not reliable. They will move around, so we don't often see them in specific locations. But once again, it's the only other option in this particular case. So we're going to say that that A is very much likely the carboxylic acid proton. Now, one thing we haven't addressed is whether there is a chance that there's actually 2 carboxylic acid presents. Maybe we have this kind of symmetrical structure where there's one pointing to one end and one pointing to the other end. But to confirm that, we can easily go to the mass spec. We can assume the lowest ratio and say, well, let's say that there are 2 carbons based off of our carbon NMR, which would give us then 24. A carboxylic acid is going to have 2 oxygens. So 2 oxygens will give us 32. And then if we think about the number of protons, we can count them down here in the table, assuming the lowest ratio again, and we can say that there are 4. So 4 hydrogens equals 4, and that would then give us a total of 60, which we can see here matches that molecular ion peak and the mass of our molecular ion. So we are all good. There is just 1 carboxylic acid present. Now, we've pretty much confirmed these, but once again, going to go through the motions to make sure we've covered everything. If we come to our infrared spectra, it looks very messy in this particular case, and there is a good reason for that. But there's a couple of peaks I want to point out. So we can disregard this kind of fingerprint region over to the side. We know that we're going to have, a peak around here, which will be our carbon-hydrogen bend. There's a peak that's probably within this that we can't see, and that's going to be our carbon-hydrogen stretch, but it seems to be kind of swamped by this really big broad peak as well. We'll come back to that one in a second. The other notable peak is here at about 1650, and that's going to be our carbonyl peak, so our C double bond O. So normally whenever you see, if there's a carbon double bond oxygen present, you will see a strong peak in that region. Now this broad peak, I'm going to change my color to emphasize, let's go green. This broad peak that we see kind of here, right? If you see a broad peak like this, it's very indicative that you have some kind of functional group that can do hydrogen bonding. And the reason it's so broad is because hydrogen bonding can occur in a large number of ways, meaning that there's minute differences between the kinds of infrared interactions that can occur. So rather than a nice sharp peak like the carbonyl, where there's only really a small number of interactions it can do, the way that it bends or stretches, for OH, so an OH in a carboxylic acid or an OH as an alcohol, it can undergo hydrogen bonding, and therefore it's a very broad peak. So if you see a broad peak around the 3.5 to the 2.5 region, it's probably going to be an OH. All right, so let's come down to the bottom, and then let's propose our structure. We've confirmed that there's only 2 carbons. We know it's a carboxylic acid, so it should be no surprise that that is pretty much the only option it can be when we have so few carbons. And we would call this ethanoic acid, remembering that our oic is our suffix for a carboxylic acid. And then the eth is, of course, the fact that there are 2 carbons present. And that's all there is to that one. Thank you.